In today's session, I'm going to go through the three stages in our e2e testing that we touch most often during our development, and show how to separate those stages and debug them separately to make things easier. First, let's look at the three stages. The e2e test framework starts from this main.py file. And if you look into here, there's a run test method that would run each test according to the configuration. So the configuration is parsed at the start, and the one we use most often, and the e2e test run in CI build is using the ref backend. So if we look at the Linode on Tensor backend test config, in this class, there are two important methods. One is the compile, the other is run. So just as the name states, the compile will compile the Torch-script module, and the run will load the thing we compiled into the runtime and actually really run the program. So most of the error we see in our development are compilation errors that happens in the compile method. So the compile method would first import the Torch module as an MLIR module. And so this import module here will call into the C++ importer. First, it would actually go to the iValue importer. Here, iValue importer. So in this class, there are import module, and import module will eventually call into import method and import tensor. And eventually, this will call into the node importer. And node importer, there is an entry point, and this is essentially where the real magic happens, that how we transform a node in the Torch script IR into the node in the MLIR IR. Yeah. So that's the importer part. And if we go back to the test config file, and the next stage after we get the initial MLIR file, actually in the e2e test framework, we won't get the file. We get an in-memory representation of the MLIR IR, and we would pass this IR to the path manager. And the path manager will do transformations on the MLIR nodes and IRs, and this second stage covers the transformation from the initial MLIR to a form that will be accepted by the backend. For example, it will lower it to lineage dialect, and also transform the torch tensors into value tensors to make sure the IR will be in acceptable form to the backend. So this is the second stage, and the third stage is that we actually pass the IR to the backend for backend compilation. So in our case, we are using the reference backend, and the reference backend will continue lower the IR to the real LLVM IR and compile it to binary. So that happens at the backend transformation pipeline. And yeah, those are the three main stages. Usually, the arrow we see are in the first two parts. We rarely need to touch the third part, except for the bug, the return type issue Daniel debugged the other day. Yeah. So now we can look at how does the failure look like in those stages. Oh,
I have a question before we do that.
Yeah, sure, go ahead.
Where are the entry points to the C++ code exactly in that? Is it the module.operation.get ASM?
Module.operation. This is actually just this is not the entry point to the C++ code. It's this get ASM is just to get the IR.
Okay.
So this is at the second stage. So from the importer stage, we already get the IR, and this get ASM is just to get the IR that we imported.
Okay.
And the entry point, you can say it's here, it's import module, but it's hooked up with a C++ side through pybind. That part I'm not familiar either, but somehow when you call this Python method, pybind will do the magic and bring you to the high value importer. Yeah.
It just works.
Yeah, I think.
Yeah, a lot of the Python methods just have just wrap a C++ function.
Yeah.
Right.
I forgot where is. There is an interface that pybind use that you specify. Or when I call this Python method, I'm actually calling this C++ method.
Yeah, and I'm sure that he's going to go over it, but a lot of times when you run the test, if you run it with the verbose flag, it'll give you the temporary MLIR file so that you can run the Torch-MLIR opt directly without running the test again. And you can,
Yeah. I'm going to I'm going to talk about that a little bit later. Now, now I would like to show how I usually run the e2e test. So normally e2e test is just a Python command. So if you look at if you look at this Torch e2e test, it's essentially just a Python command. And to simplify that, to simplify some typing, I create an alias in the bash, and I call it NPC because the project used to be called npconf, but now the name changed. But anyway, this is an alias I use to run the e2e test. So here's an example. If I run this test, then you can add the test name as filter very conveniently, and it shows it passes. So now let's inject some artificial failures in the module importer part. So if I if I insert something non-pointer and access it, and try to make it crash.
Does your alias also build the project again?
Yeah.
Okay.
Yeah.
Oh, I see. I see.
Yeah. So this is it's entered to the correct folder as well, so that you can type it anywhere. Not in the source. Not necessarily from the source, and also this is the here's the part that build the relevant part and run the Python command, so that whenever you make any changes, you just run the command, and now you can see the path disappeared. So although there's no failure printed out, you still need to be alarmed something wrong happens. It's just it doesn't print out any useful information. And in such case, I would run the command in LLDB. So I just use LLDB, point it to the Python. And the nice thing about LLDB is that it can remember all the commands you typed even after you quit the program. So if I search for, actually, this is not the program we would like to run. It's actually doesn't matter. It's in the module importer stage, but just for consistency, this is a command we run the e2e test, and we run it in LLDB.
Yeah, I really need to try out LLDB. I've only been using GDB because it's what I'm used to.
Yeah. I only start using LLDB recently, and I find it's very easy to adapt to.
It remembers commands? What? I'm so used to having to go find the file name so I can copy paste it into GDB to add a breakpoint, and I'm like,
Yeah.
You got to do the thing where you just write it all up in a notepad. Just keep it open in another window.
Yeah. I find LLDB is better in this respect. Yeah. So here it finds the artificial ceiling point we injected, and if you look at backtrace, it gives you much more information than the original command here. So that's this part. Yeah, usually the bugs in the importer are very straightforward to debug. So now let's look at failure from the second part when we really do transformation on the IR. And the test I run was for layer norm. So I just inject artificial failure here to make the transformation fail. And also let's delete make sure the other artificial failure is deleted. And now we run the command again. This will probably take longer.
I'm getting flashbacks to before I started using LLD, and every link would take 20 minutes.
Yeah. Linking takes a long time.
Also, it would sometimes crash my computer because it needed more than 8 gigs of RAM, and it would eat it all.
Yeah. What else we can look at? Yeah, we can look at the file. Look at the test config file while waiting for it. So here is a part we are actually running. We were hoping to run and fail. So if this part fail, you can see if exception happens. It should dump the initial IR file into pre-decide into the temp path. And for myself, I sometimes would like to look at the log even when failure didn't happen. So I changed it to always dump the IR, no matter what, just for convenience. And also I specified the file is from front end, so I won't get confused when the failure happens and I see a MLIR file and I got confused, not sure whether it's from front end or back end. Yeah, that's this part. And now the failure happens as we expected, and it also tells you the command to reproduce the failure. But the error message is not that useful. It only tells you there's something wrong with this operation, but you don't know the whole IR, and so it's not that helpful.
Yeah.
And
yeah, see current operation, and then there's no dump of the that operation isn't listed anywhere in the error. So you're
yeah.
I would love to see that. I would love to see that line. Where's it?
Yeah, no previous or next one, just okay, this one. And so if
I think it's more asking you, like, do you see the current operation? Because I sure don't.
Yeah, so okay, another linking is happening. So I also alias the Torch-MLIR opt to save you find the path to the command. Yeah, this where I define the alias the code that when you make changes, it will do it as well. But it's gonna take a long time, but so I will skip this one. The point is, when you type this command, it will print the same thing as before, and it's still not useful. So I try to add another alias for that. There's a command, MLIR command, that I use very often, almost always use this one, print IR after all.
Yeah.
Dump out the IR so that it's easy for you to see what each transformation does, sometimes even for just education purpose. And I always does that. And but that one only prints you out the IR before and after. Sometimes the after IR is wrong, but it doesn't tell you why it's wrong, how did the transformation end. So that's where the dash debug would be very helpful. So I simplified it to just dash D and point it initial IR file, and I always dump it into the entire output into another file. And let's wait. Yeah, and while waiting, there's another option that sometimes can be useful, but also you can run the command in LLDB to see the backtrace as well. So, okay, here this command finish. Let's look at the output. So if you go to the end of the file, it will tell you the end IR, it failed, and also the same error message. And what's more important is debugging information it prints out. So if you go to the file, search for first after is a transformation will failed, and the second after from the bottom is the IR after the previous transformation. That means it's the initial IR of the transformation we care about. And starting from here is debugging information dumped. And so you can see it's going each section is one operation, and the first operation is the function. So in MLIR, function is also operation. And so here there's a second operation is actually the first operation inside the function. So it just goes through dump detail about every instruction. And the operation we care about is layer norm that didn't got transformed. So we can see here's the debug info for layer norm. And first is try to fold the operation, but we don't have a folder for it, so this one failed. and then it would go to the go through the pattern list to see which pattern would do anything to convert this operation. And we can see for their norm first, it's always the type conversion part, convert the torch type to built-in types. And then because we insert the artificial failure pretty early on, so here you can see the failure we inserted, and you know, okay, why this pattern failed. So then you can look at the code and see where the failure from, why the error message is printed out. And from LLDB, you can also find more useful information. It's very simple to. It's the same thing as GDB when you set debug point. Yeah. And also it remembers the command I run last time. And yeah, so here you can print out the instruction, and you can print out any value. So it's pretty, I think it's pretty nice to be able to get those information.
Yeah.
Yeah, I think that's it. So for the third stage, when the backend path manager do transformations, the debugging process is actually similar to the second stage. You all just need to use the Torch-MLIR opt command plus some pipeline option or transformation option, and to run the test very standalone rather than from the PyTorch side, Python side. So it's quite convenient. So
yeah, I've noticed that running GDB on a Python program is not exactly easy because the backtrace kind of doesn't mean anything with all the reentry points and stuff. It's really hard to follow the backtrace.
I see. I think, yeah, LLDB, I think it's pretty nice. The backtrace still makes sense. Yeah. So yeah, that's that. And sometimes there's a sometimes when you finish the implementation and you see the result is incorrect, and you try to find if it's your algorithm that's wrong or it's some instruction you generate not do the correct thing. When that happened, I sometimes would go to this reporting.py file and look at which method. Okay, in the evaluate outcome method, and here is it compares the golden result with your result. Sometimes I would use very simple like rank 3 tensor and just print out the tensor to look at the actual content and try to compare the result. Sometimes the failure happens, but you can able that values are similar. It's probably just because we require the accuracy we require here is too straight. So sometimes you can just lose the requirement here, and sometimes if it still don't make sense, then I would copy the tensor into Excel and try to calculate the result from Excel. And
Gotta love floats.
yeah, and yeah, that's it. I think that's everything I find convenient while debugging the program. Do you folks have something you find that's very helpful that you'd like to share?
I've made a bunch of scripts that are similar in spirit to your aliases, but they're a lot dirtier.
Yeah, scripts are really helpful. Save you a lot of typing. Yeah.
They do until something changes in the build process, and I have to dig through a whole bunch of scripts to try and figure out which line is wrong now.
Yeah, especially at the Earth moving, changing stage. Yeah,
I spent like 3 hours yesterday trying to figure out a problem. It turned out I forgot to start the virtual environment. So
yeah,
tracking that.
That's the same experience for everyone. Yeah.
Oh, hey, it says the module wasn't found. I wonder why. Oh.
Yeah. Okay. Let me stop the recording.